Today we're going to do exponential decay. So the formula, everything's pretty much going to be the same as yesterday, except we're going to look at decay instead of growth. So your equation is still y equals a times b to the x power. What was the a? The starting point. What was the b? The growth factor. Now, yesterday, since we did exponential growth, it was 1 plus the percent. Since we're doing exponential decay, what do y'all think it's going to be? 1 minus the percent, if you're looking for that number. All right, it says, tell whether the table represents an exponential function. If so, write a function rule. So basically, whenever you're looking at an exponential function, you're looking to see that the same thing is happening all the time. And you can kind of see from 27, how would they get to 9? Yeah, so you're actually like multiplying by 3 because it's 1 over 27, right? So you're multiplying by 3, you're multiplying by 3. Multiplying by 3, multiplying. So do y'all see the same things happening throughout the whole thing? Yes? Okay, so does this show exponential growth or decay? The answer is yes. And if you want to write a function, what do? You're going to go to stat, and then you're going to use your calculate button. So let's go to stat, edit. So -2, -1, 0, 1, 2. And then I need alpha y equals 1 over 27. So once you have your table in, what are you going to hit? Stat. Calc, option 0, and there is your equation. Now, what is 0.3 repeating? 1/3. So you're going to have y equals 1/3 times 3 to the x power. All right, look at the next one. Let's see if it shows exponential growth or decay. What would you multiply by to get from 8 to 4? What would you multiply by? Thank you, a half. So by a half. How would you get from 4 to 1? You would multiply by a 4th. Okay, so did the same thing happen? So this does not show exponential growth or decay. All right, at the bottom, it wants you to graph, but we're not going to graph on these. We're just going to fill out the table. But it wants us to fill out the table for the function and then identify the domain and range. So where would I go in my calculator to fill this out? So I would go to y equals. I would put in 1/2, tab out to the x power. Okay, and then I'm going to go to my table, so second graph, and I'm simply going to fill it out. So -2 is at 4, -1 is at 2, 0, 1, 1 1/2, and 2 1/4. Okay, if I want to see the domain and the range, where do I go? I'm going to go to my graph to see what's going on. Remember that the domain is the x's, so you're looking on the left. Going left, is there going to be a minimum? Is it going to stop, or is this going to keep going? Okay, how about on the right? Is it going to stop or keep going? So what is my domain? All real numbers. What is my range? So let's look. On the y-axis, is there a minimum? Like there's a point it's not going to cross. What is it? 0. And so since it's going above, what is my range? Y is greater than 0. Okay, try the next one on your own. Everybody should be doing it. You don't have to in that one, but I mean, if you're ever concerned about it, always put it the way you see it. Okay, did you fill out your table like I did? What was your domain? All real numbers. What was your range? Y is greater than 0. Good. Okay, let's skip the next two because we've already done enough of those. Let's go down to the bottom and let's go compare Actually, let's go, I have a better idea. Let's go do this one since it's all on the same page, and then we can actually see what we're doing. Okay, so on these, if I want to compare exponential functions, what's the first thing I need to do? Fill out my table, right? All right, so here we go. Y equals... And I'm going to put in 1/4 to the x power. And I'm going to go to second table. So when it's -2, what is y? 16. When it's -1, 0, 1, 1, 1/4, which is 0.25, and 2, 1/16, which is what? 0.0625. And I only put that in decimal form since I'm about to graph it and I want to make sure I know where it goes on the axis. All right, so for the next one, I need 1/3, tab out, open parentheses, times 1/4 to the x power. Go to my table. 5.33 repeating. -1 is 4/3. What's 4/3? 1.3 repeating, yes? 0, 1/3, which is 0.3 repeating. 1, 1/12, which is 0.083 repeating. And 2, 1/48. It's easy to graph. Once it what the problem is once it gets really, really close to 0, remember it's never going to touch 0, so the number's just going to keep getting smaller and smaller, but closer to 0, closer to 0. All right, so the next one, -1/3. What did we learn about this yesterday? Yeah, it's going to be the exact same numbers as this, right? Except negatives. But let's go check. Oops, I didn't mean to hit graph. Like reset it. 2nd plus 7, 1, 2. All right, so does everybody see that it has the exact same numbers as this one, but they're all negative? All right, now we can go graph them and we're going to compare them. This is the one that we're going to really compare them to. Am I going too fast or y'all okay? Okay, so we're going to go graph this one first. So negative 2, 16, if it fits on the graph. So it'd be somewhere right in there. Negative 1, 4, 0, 1, and then it's going to really start hugging that x-axis, 1.25 and 2.6, so something like that. Remember, exponential functions, once they approach that axis, they never touch it. They just get as close as possible to it. All right, so this is y equals 1/4 to the x power. That's the one we're going to compare them to. The next one I'm going to graph, I'm going to do in black. So I have negative 2, 5.3. Negative 1, 1.3. 0.3. And then it's going to hug that. So what is this? If I was to compare these, is this a vertical shrink or a vertical stretch from this red one? It stretched it out, yes? It made it wider. So when I start with y equals 1/4 to the x, that's the one I'm going to compare. Then y equals 1/3 times 1/4 to the x is a vertical stretch. Y'all understand why it's a stretch? It's like I took this line and I pulled it out some. Stretched it out. Yes? Like from here, you're stretching it from that axis. Okay, now I'm going to do the other one. I'll do it in black as well. So I have negative 2, negative 5.3, 0, negative 1, negative 1.3, 0, negative 0.3, and then it just starts to really hug that line. Again, we're still comparing to that original red graph. So what happened when I did negative 1/3 times 1/4 to the x power? The first thing it did was a vertical stretch. And then what did it do? It reflected, so a reflection across the x-axis. Okay, if you would, flip to this last page right here at the bottom, and let's look at the word problem. Where it says exponential decay model, that's the equation that we've been using for exponential functions. So what is our equation?
Y equals a times b squared to the x power.
To the x power.
Squared is 2, you want? Like 9.
If you say squared, you're telling me the exponent has to be 2. So to the x power. All right, remember A is the start. B is the what? It's the growth factor. You can also call it the growth rate. So I just want y'all to know it could be called either thing, the growth rate. Now, when you're looking at, I need y'all to listen because we're going to write another thing over here. This equation, when you're looking at time and stuff like that, can be looked at slightly different. You could look at it as y equals a, and y'all remember how we said to find the growth factor, you do 1 plus the percent or 1 minus the percent, right? Since we're learning decay, what am I going to put? Okay, the percent, and the exponent is going to be the time. Isn't this the exact same formula as this? This is just telling you how you find that growth factor. All right, so let's look at this word problem. It says the number of acres of pine forest decreased in the western U.S. from 1963 to 2002 by 0.5% annually. Did y'all see something? I saw a percent. And anytime we have a percent, what do we have to change it to? A decimal. And just because it has a decimal does not mean it's a decimal. If it has a percent sign, it's a percent. So how do you change a percent to a decimal? Move it 2 places to the left. All right, so 1, 2. So it's going to become 0.005. So that's going to be the number that I put right there for that percent. Yes? All right, in 1963, there were about 41 million acres of pine forest. What did they just give me right there? That's the start. How much pine forest was there in 2002? All right, let's start to write our equation. So I need an A. What's my start? 41. Can we just use 41 and then in our answer write million? All right, so 41, open parentheses. How am I going to find that number? 1 minus 0.005. And now we need to figure out what the exponent needs to be. We need to know the time. So it says, how much was there in 2002? What are we going to subtract? The years. 2002 minus 1963. So put that in your calculator. 39. So that's my exponent. And then I'm simply going to type that in. Now, could I have gone ahead and done 1 minus 0.005? Yes. But I could also just leave it like this, and I could do 41, open parentheses, 1 minus 0.005, close parentheses, to the 39th power, and that's 33.7, and then you have to remember to put that million on there. Now it says, if this trend continues, meaning if it keeps decaying at the same rate, how much pine forest would be left today? Well, what year is today? 2022. So I'm going to use the same formula. I'm going to do 41, open parentheses, 1 minus 0.005, but this time my exponent's going to be different. I need to do 2022 minus 1963. Or you could do that, yes. All right, so let's go type that in. $30.5 million. And so you can see that the number of acres of pine forest is rapidly decaying. Yes? All right, let me pass out the. Okay, so for the assignment, let's do 1 through 18. Now, can y'all please listen? On number 18, those are not answer choices. It says, find the value of the computer for the given year. So you're going to find it for 1 year, 3 years, and 5 years. That's what you're going to plug in for the value of x in your exponential function. Does everybody understand? So the first one, once you write your function, you'll plug in 1 for x. The next one, you'll plug in 3 for x. Now, on 15 through 17, how do you know if it's showing exponential growth or exponential decay? It's how the graph is shifting. So if I'm starting over here from left to right and I am just totally going down, what is that? That's exponential decay. So but look at 17. On the left, I'm starting at nothing, and then I'm rapidly increasing. That's what? That's exponential growth. It doesn't just say that, though. It says, tell whether the graph is showing growth or decay. So number 15, you're going to write decay. Then it says, write a rule. Well, did it give you some coordinates?
Yes.
Could you go in stat
Yes.
and put that in? Yes. And then option 0, enter, enter, enter. Everybody good? All right, again, we're doing 1 through 18. And make sure that you are reading the directions. Like 12 through 14 says, graph the function. Then compare it to this function. So you probably need to graph that one as well. Make sense? All right, get busy.